Let's see, do we have video? Are we doing video? Yeah. Okay.
All that weird talking on there. That's great. Anything I can help you with, friends? Questions? We have the Euler's method web work out. I've got your homeworks from the written ones. I'll have those back on Wednesday, and complete solutions. But is there anything I can help you with right now? Anything in general you want to talk about that would be useful? Cool. When is that web work due?
Tonight, I think, right?
Is it tonight? Does anybody need more time? Okay. All right. You can just go like, give me a little thumbs up, secret thumbs up. Okay. All right. Cool. Great. Well, I can't wait to talk about mixing shit now. Fantastic. So let's start off today with an application. And we'll see how well I can do this, because it's like chemistry stuff. So we're gonna start off with a vat of brine. We're making some pickles, a lot of pickles. So got this tub, and there's a bunch of fluid inside of it. And it's a cylindrical drum. In fact, it's a 100-gallon tank. And right now, it's at 50 gallons. Bless you. So that says 50. 50 gallons is where we're at right now. And there's salt and water in there. And the water, we're just assuming, is pure H2O. And it is being pumped in. So we've got a little inlet here that's just shooting brine into this thing at a rate of 5 gallons per minute. So the input is 5 gallons per minute, and we need to know something about the brine. There is 1 pound of salt, whatever your favorite salt is, per gallon. So 5 pounds of salt per minute. If we just starting to make sense of what's happening here. So we're putting in 5 pounds of salt per minute, and simultaneously just 5 gallons of water per minute. Good to note. Originally, when we first started out, before we turned on this valve and had all the new brine coming in, we had this 50 gallons, and there was 5 pounds of salt dissolved into this. So 50 gallons at 5 pounds of salt. We also have an outlet at the bottom. And so there's a little tube that comes out here. And out of this tube is coming 4 gallons per minute. And we're gonna assume this is well mixed, that by the time this comes to this part of the tube or this tank and it's coming out, everything's totally mixed. There's no, in other words, this is a homogeneous mixture. The density of salt doesn't change depending on where I'm at in the mixture, in particular as it comes out. So here's our question. How much salt is in the container when it's full? Question. And you can see, let's just talk about when it's full. There's 5 gallons per minute coming in, there's 4 going out. So it's definitely moving up at a gallon per minute, right? So after 50 minutes, this thing will be full. So just a few notes. So 1 gallon per minute is the net influx of water, of fluid. In other words, 5, let's see, what do we have here? Yeah, 5 pounds of salt per minute. So just 1 pound of salt per minute coming in. No, wait, where am I getting that? What am I doing wrong here? Oh, right, there's still 5 pounds of salt coming in, and we're not quite sure of what is coming out. That's what we got to figure out. So let's get some variables. Let's let x of t equal the amount, and this is all in, you know, goofy English units, but that's what we got. Amount of salt at time t. So notice how all the information is given as a rate of change, right? I'm given how fast the salt content is being increased, and I'm also able to determine something about how quickly the salt is dissipating from the solution or being removed from the solution, and as well as water. So what we need to do is turn this into a rate of change problem. So x dot of t equals the rate of salt, what is it? Rate of salt. That sounds weird. Can somebody help me find some better language?
Salt growth.
Yeah, I like that. Thank you. Yeah, that's perfect. Salt growth per minute at time t. And from here, we're going to create a differential equation. So this rate of salt growth, that's perfect, thank you, is equal to the amount of salt coming in via that top tube minus the amount of salt leaving. That word is coming in. So help me out here. Let's start pulling some stuff together. What is something we know? This will be in pounds per minute, right? So this is all going to be pounds per minute. Is there any of this that's low-hanging fruit?
With the salt coming in.
Yeah, how much?
5 pounds per minute.
Right, yeah. We know right up here that 5 pounds per minute is coming in along with this water. And notice this doesn't speak to volume. Volume isn't mentioned in this particular equation we're going to create. So that's equal to 5. That doesn't change. That's a constant rate of influx. Now we need to come up with the amount of salt leaving. Well, let's think about it. So we've got, so how much salt, how fast is salt leaving? And let's just do, the way I used to do physics, and probably everyone still does, is try to find the units that cancel the right way and do that stuff, right? So we know, isn't that what physics is all about, just canceling units and figuring out, I know there's more to it than that. Dr. Gray, if you end up ever watching this, I know better. But check it out here. So we've got 4 gallons per minute leaving. How do I figure out how much salt is in each gallon? So what is the concentration of salt per gallon? What is the current amount of salt?
5 pounds.
What is that? What's that?
5 pounds.
5 is the influx, but it's not what is the true amount of salt in the tank at time t? Let me pull back from that question. Ask it a different way. How much salt is in here at time t?
50
10.
pounds of salt, because there's 1 pound of salt per gallon and there's 50.
At the initial moment, yeah, but like at time t, as this changes, it's not a number, it's a thing written on the board. How much salt is in the tank at time t? Right here. That's just x of t. This is changing all the time. There's salt coming in, there's salt leaving. We don't know. That's what we're actually trying to find. We only know at the very beginning, Lou. So when you were given that, that's the initial conditions, and we got that, but it's going to change. So the amount of salt leaving is going to be X is the pounds of salt, X at T, let's just put X at T, and let's put at time T here so that it's clear. So this is the amount of salt at time T divided by the volume. So this is pounds of, and then I'm gonna introduce this variable V. This is the current volume of water. At time T, so check it out, the units are gonna work out perfectly here because I've got 4 gallons per minute times pounds divided by gallons. So this is gonna be in gallons. What I'm gonna end up with here is pounds per minute when I do all the math. It's just this volume I need to figure out. What is the volume at time 0? So let's talk about volume. So volume at time 0, how much is in there then? 50, right? We started off with 50. So 50 gallons. How is that volume changing after that as time moves forward?
Minus 4T.
What was that?
Minus 4T.
Minus, ooh,
Oh no.
you're
Plus
thinking
1
too
T.
far ahead. Yeah. It's just 1 gallon per minute, right? That's the net outflow because, net inflow. We've got 5 gallons coming in, we've got 4 going out. So the net fluid gain, let's just write this up here, is equal to 1 gallon per minute. So each minute that goes by, another gallon has accrued in the tank. And let me stop and make sure that that sounds good, but I'm gonna take 50 plus, so the initial, plus 1 T. So this is 1 gallon per minute increase, and then my time will be in minutes. And this is in gallons. So I've got a diffie-Q right now, and let me know if there's any problems. Any of this needs a little bit of clarification. And if not, we've got a differential equation. X dot equals, where did I put it? Oh, so intake minus outtake, whatever, I'll just call it that. Intake minus outtake, that is equal to 5, which is a fixed intake of 5 pounds per minute, minus this creature that I just created over here, which is 4 over 50 plus T, X, and we're good to go. And we've got an initial condition, X at 0 is 50. No, wait, what is X at 0? 5, thank you. We actually say that, right? This is X at 0, 5 pounds of salt. So we've got a differential equation. Let's write it the way we like to write these things, which would be X dot plus 4 over 50 plus Tx equals 5. And then we've got the initial condition. I want to solve that. Is that separable? The answer to that is no. Oh, sorry. What did you say, Cormac? Yeah, you were coming up with that, yes, sorry. So this is not separable. We need a new way to solve differential equations. If I didn't have a new way, what could I do to study this problem? What are some things I could do? Draw a graph. I could make a D field, make some estimates. What if I wanted a precise approximation of how the salt changes as time moves on? What could I do? Euler's method. So we could do Euler's method, improved Euler's method, any numerical method we could do, but we're gonna do one better today. This equation is called a linear differential equation. And so that's what I want to talk about today, linear DEs. Because they come up a lot. So I thought it'd be cool to start off with at least just, an example. I don't do enough examples maybe in here of applications. but we're gonna solve that sucker today. So the setup is this. We are given a differential equation of the form. I'm gonna write it both in x and y's and in t and x's. But we've got something that looks like this: y prime plus some function of x, y equals some other function of x. So that's y there. And we've got an initial condition, you know, y at 0 equals, or y at x naught equals y naught. Or it looks like the one that I've just written, and it's x and t. It doesn't really matter how that looks, it's the same rhythm either way. So let me stop for a second, let you get caught up writing. Eat a jelly bean. Cool. So how do we solve this? There's a trick. And I want to just show you the trick because you wouldn't guess it on your own. So let's think about a cool mechanism for making this problem actually pretty straightforward, because it doesn't look like that now. So a trick is needed that relies on the following. I'm going to just do an observation, following observation. Let's do this for x and t, since that was our original problem. If I take the derivative with respect to t of e to the integral p of t dt, so that's an exponent that is the antiderivative and antiderivative of p, times x of t. How do you differentiate that? What's the most fundamental rule that I need? May help me out. How do you take the derivative of a product? The product rule, exactly. I'm trying to be a little suggestive there. So we use the product rule. And it's going to be the derivative of this first piece times the second piece left alone, just good old x, plus the first piece left alone, times the derivative of the second piece, and there's our x dot. Cool. Let's finish up a little bit more. What is this derivative? Right here. Somebody help me out. Same thing, except I multiply by what? The derivative of the exponent. So for this one, this is a little quick refresher. If I take the derivative of e to something, that's equal to e to that something times the derivative of that exponent. Really important rule for us. So that's the one I'm going to use. So this is equal to e to the integral p of t dt times the derivative. Let's just write it out for a second. That's starting to look really cool. Product, there's three things in this product, plus e to the integral p of t dt times x, and that, we don't need to write of t, there's enough shit going on here. So we'll just put x down right there. Can somebody help me with this?
Is that just P of T?
It's just p of t, right? Think about what these things mean. This says take the antiderivative of p, then take the derivative of it. This is just p. These two undo each other. They're inverse operations, kind of, in calc. So this just equals p of t. And so all together, what I've got is, and I'm gonna write this in a slightly different order. E to the integral, I'm gonna put that first, P of t dt times x dot plus e to the integral P of t dt, P of t times x, and we've got what we need. And what we're gonna do is compare this to the left-hand side, the LHS of our original problem. Right over there, I'm gonna call that star. It sure looks a lot like star, except for this e to the integral thing. So let me just pull back here and show you what I mean. If I take this left side and multiply by e to the integral P of t, here and here, then it looks exactly like that thing there. But I don't get to just multiply one side of an equation by something. So the left-hand side of star looks like this. It's x dot plus P of t. Maybe it'll help to just put it here. So that's the normal left side. So in other words, to make that thing, that left side, look like this, I'm going to multiply both sides by this factor here. And then the left side will become this. So take our original, multiply by e to the integral P of t, looks like this. That is equal to this, is equal to this, is equal to this. So what I'm going to do is multiply through by this thing called an integrating factor. It's going to make the left side become this, and we're really close to just knocking out the final solution. So, in other words, let me summarize that. All right, to solve, summary. To solve, x dot plus P of t x equals Q of t. Initial condition also. Not a problem right yet. Multiply each side by e to the integral P of t dt. So you take whatever's in front of this x, it's some expression in t, might even be a constant, raise e to that power. This is called your integrating factor. And which allows the left side to compress. In other words, after I do this, the left side is just d dt, integrating factor, x equals, and then I multiplied the right side, so it was q of t e to the integral P of t dt. So let me stop. Make sure you're following. And it'll make a lot more sense when you actually do it. This will look very abstract, but we want to have a good rhythm set up. So over here I've got a derivative with respect to t. I'm just going to integrate both sides with respect to t. So integrate each side with respect to t. The left side miraculously turns into this. Oh, dt. And the right side becomes pretty horrific looking, but kind of cool also. Might not be used to seeing so many integrals within integrals. It looks groovy. And we'll tack on a plus c right now. And then I'm going to multiply each side by e to the negative integral P of t dt. In other words, divide both sides by this thing. And what we get, so divide by t to get our solution. Check this out. X of t equals something that's going to look even worse. Awesome. Outstanding. Look at that shit. Now we got some math going on. My God. Woo! Plus c e to the negative integral p of t dt. We're done. And then find c using the initial condition. We're not going to work that out here. So use initial condition to find c. And you're done. This part here is called the particular solution. It's the part that is going to give us the right-hand side. So that q that comes out, this is going to give the q when you run this through the differential equation. When you do that left side up there, the x dot plus p of tx, if you take just this piece and do that to it, you'll get the right side. This side is the homogeneous solution. Homogeneous. So if math folk, if you're making milk, you'd probably call that homogeneous or something. You can say it however you want in math. Homogeneous or homogeneous. Homogeneous sounds like, you know, kind of British, slick, cool way to say it.
Homogeneous.
Homogeneous, that'll work too, because everybody know what you're talking about. Let's solve our original problem. So let's come back to the problem we had, the salt solution thing. And this is really all I wanted to show you today. And then there's a web work that'll open up shortly. So example, solve. There's a couple tricks that you're going to want to check out here. What was this a 5? Thank you. Cool. And then we had x of 0 is 50. So first step is to make sure you have a 1 in front of the derivative. If I didn't, I would divide through by that. So make sure, bless you, you have nothing in front of the derivative. And if, like I said, if you did, divide through by it, and it'll affect everything in the rest of the equation. So step 1 is to identify to find the integrating factor. So this thing here is my p of t, and my integrating factor is going to be e to the integral 4 over 50 plus t dt. Can you take a minute and do that for me and simplify it as much as possible? This should give me plenty of time to run to the restroom, because I think it's going to take a little work. How simple can you make that? think you're doing a couple. How did you get there? Oh, boo. Boo. No robots. The technology, like you're missing, yeah. Your technology is good, right for the final answer, but it ain't right for, it's actually not what this is equal to. We don't, and don't put the plus C in yet. That, and I saw that you were doing that, but does this look okay for a first step? You know, I'm using this form here, du over u equals natural log of u, and here u is 50 plus t. So I'm using that rhythm. Leave that 4 out in front. Then this, you're going to use this identity more than any other time in this class. Oops, calm down, buddy. ln of that equals that. That these two functions are inverses of each other. That's an L, by the way. Good Lord. But I don't quite have that yet, so I still need to bring that 4 up. I have to have everything inside the log. So this is equal to e to the natural log 50 plus t to the 4th, where I'm using this property. K times the natural log of something is the natural log of something to the k. These two properties in this game, all the time. These two. Can I stop? I'm gonna stop for a second. Everybody cool, please follow, please let me know if we need to clear up any problems. Happy to, you know I am. I hope you know by now. I'll talk about this stuff forever, 10 times over, it's all good. Okay, all right. So this turns into a beautiful, and check it out, it's the 4th power, so we can get rid of the absolute values because it's always positive when we have an even power. Look at that, there's our integrating factor. Cool. So now, let's think about how the rest of this unfolds, and let me know if that is all good, if there's anything you want to talk about there. So our original problem is this. I'm going to now multiply both sides of this equation by this, but you want to, so you can write that out, or you can remember why we're doing it. The left-hand side will become the derivative of the integrating factor times x, or whatever your independent variable is. And the right side becomes whatever it was times the integrating factor. That's 4. Let me stop. So this is a game, you'll just have to get used to this rhythm, but it's better to understand why the rhythm is. And you could check this out if you took the derivative of this side. Let's just do a quick check. Just, you know, sometimes it's good to see this stuff forward and backward. I would use the product rule. That would become this times x plus this times x dot equals 5t plus 50 to the 4th. Divide both sides by t plus 50 to the 4th, and you get back our original equation. Right? So if I go through here and I divide by this quantity, I'm going to get 4 over t plus 50x plus x dot equals 5. So notice that this is still the same equation, it's just now we can actually do it. So I'm going to erase that in a second, but check that out, that just go right here. So in other words, the step that I have right here is the derivative of the integrating factor times x equals integrating factor times whatever was here. And after you do this a few times, you'll totally be rolling with it. So let's clean this up, because this was actually taking us backwards. But I was just proving to you that what we did is the same as what we started with. Now I integrate with respect to t. So the left side becomes t plus 50 to the 4th x equals, then we're going to integrate over here. That turns into t plus 50 to the 5th divided by 5, but we have 5 times in front already. So this right side just becomes this. Tack on now plus c. And never before. Just at this moment when I undo this thing, that's when I add my plus c. And divide through by this thing, your integrating factor. So x at t is this over that, so that's t plus 50. I just got one of those left over. I'll put it in parens, so maybe that's a little clearer. Plus c over t plus 50 to the 4th. And you don't guess stuff like that, right? You don't look at that original problem and come up with that. I guess the other way to come up with it is somebody gives you a formula, but we're building the formula, right? That's what's cool here. We're building this stuff from first principles and then solving it. And then lastly, so we got an initial condition that at time 0, we had 5 pounds of salt. So I plug that in, and I get 5 equals 55 plus c over, oh, whoa, slow down, buddy. T is 0, sorry. T is 0, x is 5. Got a little excited there. And so c equals, God, who knows? Let's see. So, negative 45 equals c over 50 to the 4th. So c equals negative 45 times 50 to the 4th. And our final equation then, let's just put it all back together. So x of t equals t plus 50 plus our minus 45, easy buddy, 45 times 50 to the 4th over t plus 50. But that wasn't even the original question. What was the original question, actually? What was it we were trying to find? How much salt is in when it's full? So we still haven't answered the question. This is equal to the amount of salt at time t minutes. What time is it? How long does it take for the tank to fill? 50 minutes, because it's a gallon per minute coming in. So x at 50 equals final salt, and I guess it is weight because it's pounds. So that's going to be 100 minus 45 times 50 to the 4th over, you know, whatever. I don't know what this is going to be. And I don't know that any of us care. It's a number that we can find with a calculator. Oh shit, I kind of want to know. Could somebody crank that up for me? Blaine looks like he's calculating. Start entertaining myself while I wait. Boy, you got anything for me, friend?
It's almost 100.
So, because this is pretty damn small, huh?
Yeah.
Yeah. So, what did you get precisely, though?
99.59
5 9s?
Yeah,
Wow, okay.
might be wrong, but I'll take it.
Anybody else crank this out and get something like that? It's a little shocking, but
Cause it's basically 100 minus 45 times 5 to the, 50 to the negative 4.
yeah, agreed. Yeah, I should put that up there. Well, wait a second. No, I don't know about that.
No, that's not.
I don't think that's right. Cause this actually simplifies a lot more too. Let's see, 100
I got
minus
97.187.
97, what was it?
97.1875.
Thank you, okay. There we go. It's a little more interesting. It would have been super boring if it had just been 100 pounds. And I guess, yeah, so it's a little bit more interesting. Linear equations, my friends. You've got a bunch of them to solve. So why don't we work on them? Or whatever it is you want to work on. I'm assuming that since no one said you needed more time on the current one, that we don't. So this one's open, I think, through next Tuesday. Got plenty of time on it. But let's work on it, and then I'll come around and consult. Oh, yeah.
Could you go for the denominator from 50 plus 50 to the fourth, am I reading that right?
Oh, how did I go from here to here?
Above that.
Oh, gotcha. This is 2 times 50
Oh, okay.
in the bottom, and so I pulled the 50, the fourth, and the 2 to the
Okay.
fourth
I
part.
was just reading it.
Yeah, that's cool. Yeah, no, I'm glad you asked. Thank you. Cool. Let's crank.
It's not open.
It's not open yet? Shit. All right, let me fix that. What time does it say it opens? Does it say?
1:45.
Whatever. Huh. I don't know. I definitely set it late so that folks wouldn't start working on it before it was. Oh wait, that's not even me. Alright, sorry about that. Almost there. So yeah, it says homework 3. I guess it's like web work 3 or something. Maybe it's even 4. Pay no attention to those numbers. It says linear equations. That's what we're doing. All right, so edit. Just say 150. Should do us. All right, try that, friends. Give it a refresh and see what happens. Good? Cool. Excellent. Yeah. Yeah. I mean, if you can get it to me by Wednesday,
Well, so the first part was create this thing called an integrating factor that'll turn the left side into a perfect derivative of a product of things.
Okay.
So step one is to find that integrating factor, and here it's gonna be e to the antiderivative of 2x. So e to the x squared. And then I'm gonna multiply both sides by e to the x squared. So the right side will become 2x, e to the x squared. The left side, the reason I did that was because now it can be written as d dx of my integrating factor times y.
You got e to the x by doing integral?
E to the x, so I took, well, show me where I can write. I don't wanna write on your nice stuff. Oh, okay, great. So my integrating factor is e to the integral of this in front of that y there. 2x dx.
So that's just what the integrating factor is?
Mm-hmm, yeah. And then it just becomes e to the x squared. And that means now that this left side is e to the x squared. Sorry. How do you erase?
Is this like a little clicker?
Oh geez,
You just
okay,
hold that.
hold it, okay, that's cool. Oh neat, oh look at that, okay, cool. So it's e to the x squared times y, and then the right side is just 2x e to the x squared. So the point of finding the integrating factor is because now the left side becomes that.
And then you just do the same thing to the right side?
Well, I multiply both sides by the integrating factor, otherwise it changes the problem.
Okay.
So just remember that once you find that integrating factor, your left side's gonna become d whatever. Integrating factor times your variable, which is gonna be x or y. Here it's y equal, it's just getting sloppy if I write that there. Shoot, help me out, thanks. So now your problem is integrate both sides. So now I integrate each side, but the left side is easy.
Right.
It's just that, but now you've got some actual calc to work out where you find that from there.
Okay.
Does that sound, yeah?
Thanks.
Okay, you're welcome. And put a plus C when we integrate too.
Kind of get you rolling on the first one, just in case. You can just you don't have to look at this, but it might not hurt. Does everybody's number one kind of look like this? Yeah, okay, cool. That's the road you should be going down there. And your job will be to integrate this. And I would suggest use substitution. oh, cause you had a 5 there. So that's the right substitution, and then du, what does that say there? Oh, that's just x, 2x dx, is that a 2?
It's 5.
Where'd the 5 come from? No, let's not look there, let's just look here. Cause like I'd use this, I agree with that, this is supposed to be the derivative of that. So the 5 is kinda like a separate dude
Yeah.
chilling on the side, okay, alright, there we go. So what should it be? That looks so good.
Yeah.
Yeah, agreed. Doing good, Cormac, anything I can help with? Oh, you're working on this one, cool, so I get stuck on this part of it. Do you want me to take a look and see what's up? Cause sometimes, if not, that's cool too.
Yeah, I think we just put some.
Alright, let's take a look. So is this is our function. So where does it say you're wrong? Is this first step okay?
This one was okay.
Ah, okay.
0.4.
Gotcha.
And 2.63.
Okay.
For the first one?
7 times
I used 4. I just thought that isn't too
Huh, so notice how that is positive. That seems really wild that changed that fast. That is sus to me. So I'm thinking. So what was our original y? What is y at 0? Is it negative 30? Yeah, we shouldn't shoot up positive that much. So what happened?
It said that it was correct for 2.
Oh god, that's weird. That's insane.
Yeah.
Okay, whatever, okay, I guess it's very steep, I guess it's ridiculously steep. Okay, so let me go to, oh, I can't use my calculator.
Actually, I think I see.
You think you see it, what is?
I just jumped a step. For when I was doing this part, I was supposed to put the 2.
So easy to do,
6
got it, awesome, cool, yeah,
Yeah.
alright, ready for that to work.
To use.
How we doing here? You got anything to talk about? Are you all good?
X squared on
think
U.
That's, yeah,
I'm
so
working
good.
through it.
So then you should be.
Awesome, please do.
Cause the X cancels out.
That X would be.
Friends,
Yeah.
anything I can help with?
Should be okay.
It's just tedious, right? Like it's so tedious to go through those little guys. Okay, alright, well, I'll take that as an okay. Thumbs up. Oh man, anything I can help you with? I see a red there.
Yeah, I think I messed
Okay,
up somewhere.
you're figuring it out,
Yeah.
okay, alright, I'm here if you need me. How you doing? Everything good, or you got a question? I think so too, that looks good. Mm-hmm, cool. Oh, that, wait, so, that is not an integral we can do, so I think your integrating factor's off. Let's take a look. So it should, oh yeah, x to the 4th. Wait a minute. That. Yeah, it should be times x to the 4th. There we go. Yeah. So, yeah, but this should be a times, so it should be 9e to the x times x to the 4th, because you want to multiply both sides by that integrating factor. So, to get from here.
Yeah, but this was
Oh, right. So, oh yeah, and you forgot to bring that along, and when you multiply through by it, it does cancel out at the end. So that's what, oh, yeah, you're good. Yeah, you just didn't do that canceling. Yeah, solid. And that should be e to the 4. So that's e to the 4 natural log of x, so your integrating factor is e to this. It's e to the derivative integral of that. Yeah, otherwise it's, no wonder it was looking horrible. It's gonna look way better. Hi, Tracy.
I don't remember what I had this and I didn't have.
Uh-oh.
Let's take a look. It's just Oilers.
Okay.
Just this equation here. What am I? What am I putting on?
Well, let me take a look. Let's see, so our initial condition is 0, 3. And our function is.
Oh no, functions up here.
Oh, okay, got it. Okay, so it's the 9t to the negative y.
Yeah. So I'm not using the right
You're not,
equation.
that would, you
I see.
definitely, yeah.
Okay.
That's like problem 1.
I see.
Let's figure that out first. Did you have a
Okay.
different one you were wanting to talk about, or?
No, I just
Okay.
that makes sense.
Yeah, yeah, I think you're gonna have a lot better chance of success.
Lou, you cool?
I mean, I know you're cool. You need help with anything? Alright, okay, that's good. See, so anything I can help you with, my friend? So far, so good? Okay. How did we move from here to here?
But you took the,
So this form is just e to the u.
Yeah.
So I don't know how that got in there, because that is unrelated to this thing. You will not be using a natural log anywhere in this problem. Yeah. That is a good hint, yes. So what I would say here is, Lou, we've got
2 to the x squared plus c over to the x squared. Because this side's also multiplied by e to the x squared.
something like that, right?
Yeah, which is plus c.
I'm just looking at what you got here. Do you want me to go through how you got that? Because you got that. I didn't get that.
Well,
But yeah,
so I take this,
Perfect.
which is this,
love it.
and then you get
It's beautiful.
that,
Agreed.
and then,
It's that. Yeah.
and then the derivative of
Mhm.
this is just
Yeah.
that, and then you multiply that on both.
Right, so that's just your right side, after, before you integrate it. So your left side, you've got d dx, e to the x squared y equals this,
Mhm.
right? Sure?
Yep.
Okay, cool. And then I integrate both sides. So this becomes, I have to do this integral. This is where I ran into you when you were working on this integral.
So you have 2
Okay.
Yeah?
to the x
So
squared, right?
the only way to do an e integral generally is with this
X
form.
squared, so it would be u is equal to over 2x divided by 2 divided by 2, and 2 goes away.
So I have to make this, and I'm just gonna leave the 5 off. Look like this. So what would be u? What would be the right substitution? Lay this template on top of there. What comes through the u window?
X squared.
Yeah, exactly. So we're gonna let u equal x squared, which means, and you were doing all this just perfectly, 2x dx. And then when I solve for dx, so I wanna do the substitution, so this tells me that dx is du over 2x. So I rewrite this thing as integral x e to the u, and then dx is du over 2x. Let me stop there. Check that out. And anybody who wants to check that out, I'm happy to talk or answer questions about it. I mean, there's more to do, right? But let's just make sure we're in agreement. Let me know when you feel cool about this, Lou, and I'll show you where we go next. Yeah, and play with it. You're good? Okay, So now the x's cancel, which is good, because I don't want a bunch of different freaking variables in here.
Okay, yeah.
But I had that 2 in the bottom, I'm just gonna bring it out in front. Right, because this 2 was there, that didn't cancel.
Yeah.
Honestly, I mean, not honestly, but the reason I'm doing substitution is to get the number that should go out in front. So now, oh, it's just 1/2. Yay! Because that's just that, plus c or whatever. And then I back substitute. That's my antiderivative. Now, we still had that 5 out in front, so you'll still have 5 times that, but that's what we're shooting for.
Okay. Yeah.
Yeah? Good news, lots of practice, 8 practice problems.
Then that would be plus C, right?
Yes, yeah, absolutely. Yep. How's that one shaking out, Tracy? Oh, you're on a different one now.
Yeah, I was on the linear one. I wasn't looking at the Euler's ones, I was looking at the Euler's ones today.
Okay, cool. Yeah.
But the
I wasn't
reason-
sure if you're integrating factor.
the one my number was just 8 instead.
Mhm.
I was looking at the curve, so I'm supposed to model after this one, right? This
Mhm.
equation.
Mhm.
So from getting to like when we're on the board, that's like this step, right? And then you move to
Yeah.
this step.
Yes.
So then from here, I just need to basically get to here, hit C, and then that's it.
So I can tell that that's wrong, actually,
Yeah.
what we have there. So how did you get here? Can we look at how you got there?
Yeah, I mean, I just did, the steps you did on the board, with everything in it too. Like here, like, this is my equation.
Yeah, so your integrating factor is, so that's actually not the integral of 8x.
Oh, it's supposed to be 2 still?
So this should just, yeah, so you're integrating, you're grabbing the wrong stuff. So your integrating factor doesn't come from this right side, it comes on what's in front of the dependent variable.
I see.
So integrating factor is e to the integral of 2x dx. And even if this had been 8x here, that would have turned into just 4x squared,
Okay.
not 8x. So this is, so your integrating factor here is e to the x squared.
Okay.
And then when I multiply both sides by that, the left side will become derivative, and it'll always work like this. Integrating factor times y equals integrating factor times whatever was over there.
Yeah.
So for us, it's going to be d dx e to the x squared times y equals e to the x squared, because that's our integrating factor, times 8x. So I put it like that.
Oh, okay.
And now I have to take that antiderivative, tack on a plus c,
this side, so when you integrate, this will just become this, e to the x squared y.
Yes.
The right side will become antiderivative of that beast plus c, and then you'll divide through by this, and then you'll have your final answer.
I see. Okay. Yeah.
Okay, cool. Okay. Man, yeah, something looks painful. Painful. Okay, so let's take a look. So, that's our original. Alright, so. Oh, okay. Did this one work out okay?
Yeah.
Okay, awesome. So, negative 5t, agreed. Yeah, cool. And then the right side is, yeah, so you did great, but I have a feeling you didn't anti-differentiate this right side. Well, it should be 6/7. So when you take the antiderivative of that, then oh, I don't understand that too, where that came from, but. Yeah, there's a few, the integrating factor, but, there's a few issues here, so this side will become e to the negative 5ty equals 6/7 e to the 7t plus c. Antiderivative of e to the kt dt is 1 over k e to the kt. So that, so it's right here.
That's on the left side.
And, oh shit, yeah, you haven't you haven't multiplied by it yet, got it. Oh, I see, okay, there's all sorts of stuff floating here. Okay, gotcha. So the integrate, so that was negative 5t, now I see, okay, I'm with you now. Now I see where the plus 2t came from. Cool. So, this should be, 2, and then that's actually 6 halves, yeah, so 3t. Yeah, that looks good. But then you still have this over here, e to the negative 5t. Okay, gotcha, cool. So you should get 8t or 7t, so 3e to the 7t plus c e to the, yeah, and you could just write that as c e to the 5t. I think that probably, yeah, should be positive.
Yep. Other than that, good work. Alrighty, friends. Good stuff. Let me know let's talk on Wednesday about any issues you might be having.